This is going to be the final lecture in the series, a crash foundation course in mathematics. This will be the 4th lecture. We will mainly concentrate on equivalence relation, but we shall start with the modern abstract definition of a relation and give some examples, and then move on to equivalence relation, look at least a couple of examples. Then we will also see how an equivalence relation gives rise to a partition and vice versa. That is, a partition also gives rise to an equivalence relation. Okay, so stay tuned, and if you wish, you can see I'm going to show that this series of lectures can be followed by the notion of partial order, because MSc onwards you need that, and many students have problem with partial order. So I have gone very slow and given a series of 3 lectures on that with the good examples, okay, and applications. So if you are interested, please follow these 4 lectures by those 3 lectures. Okay, you will enjoy. Sure. Okay, let's get started. So what is a relation? Okay, so the relation is a standard concept which all of us know. What is this? I seem to have a problem. Yeah, so my tablet was not working. It went into sleep mode, I believe. Okay, so what is a relation? This is what we usually have a common thing, right? If I say X is the son of Y, that's a relation. X and Y are related. In what way? X is the son of Y. But the first thing you should notice is I cannot say Y is the son of X, because Y may be a father or mother. Okay, maybe the father or the mother of X. Okay, therefore the order in which I am giving is very important. That is X, Y. I say if X is the son of Y. So the order matters. The first person is related to the second person. That's what we are saying. Is that clear? Therefore, the modern definition of a relation, so suppose X is a set, okay, modern definition of relation is R is a subset of X cross X. Just a subset. That's it. Remember, we have talked about subsets of Partition product, right? But they need not be product of subsets. Okay, anyway, is that clear? Yeah. Now let's look at this. May look a little too abstract, but let's do that. Therefore, once I have a subset R, how do I define a relation? Okay, so this is our definition. Let a relation is a subset R of X cross X. If you want, assume non-empty, but okay. Then how do I define a relation? I want to say X is related to Y, or X or Y, where X and Y are elements of capital X, if the ordered pair X, Y belong to R. That's it. Then I say X is related to Y or X or Y. Do you understand this? Let us look at a very trivial example so that you will have. Suppose I have a set S, let's say set X equal to R, that are real numbers, right? My set R, this R is different from this R, right? This R is nothing other than the diagonal line. Now look at the diagonal line. Okay, my thing may not go exactly like a diagonal line, but I hope all of you are intelligent, you will understand. Y equal to X, right? Yeah. Now let us look at, this is my set. Okay, that is are the points above the line Y equal to X. That is my R. Okay, they should be strictly above. Points on the line are not considered. Do you understand that? Okay. Now let's look at. Therefore, if you give x, y in real numbers, then when does x, y belong to R? This subset R, this relation set R. Just look at this. If I take any point here, right, you can see its x coordinate is always bigger than, sorry, y coordinate is always bigger than the x coordinate. Do you understand that? Therefore, this happens if and only if, okay, x is less than y. Do you, okay? Just think for a minute, follow this. Therefore, this subset defines the relation of our standard less than relation. So this subset R is nothing other than the less than relation on R, standard less than relation R. Do you follow that? Yeah. So pause, review, proceed. Yeah. Just to make understand, let's go back to the example with which I started. Suppose my X is a set of people, okay, human beings on Earth, of course. Okay, and I want to say X is son of Y. Okay, so what should be the set R? The set R must be subset of X plus X. How will I define that? Notice that I want to say X is a son of Y. Okay, therefore it's ordered for S. But remember, X is a son, therefore first condition is X must be a male. And Y could be father or mother, therefore there is no restriction on Y except Y is a parent. Okay. This is ordered pair. Right? Therefore X is a son and Y is a parent of X. Therefore, how will I call it? X is a son of Y. Is that okay? Right. Okay, I can give a lot more example, but as I said, since this is supposed to be a crash course, I don't want to spend too much time on too many examples. Okay, this is good enough. So let X be a set, R be a relation on X, sorry. Okay, then this relation R is I think reflexive. Okay. Reflexive, it just reflects, that is, if X belong to R, which is same as saying that is X is related to X itself. Okay, I'm related. You follow that? Okay. So this is first good. And second, R is said to be symmetric if you tell me X, Y belong to R, then implies then YX belong to R. What does it mean? If you say X is related to Y, then I want to conclude Y is also related to X. Okay, now let's look at here. Let's look at the usual less than relation. Do you think X is related to X? No, because X should be less than X. Law of trichotomy says it cannot happen. And similarly, let's look at this here human being son of relation. Is X is related to X? No, because X cannot be son of himself, right? Okay, so it is not. Now next thing, is it reflexive, this relation? If X is related to Y, that means X is less than Y. Does that mean Y is less than X? No, 4 is less than 5, but 5 need not be less than, is not less than 4, right? Therefore, that's not reflexive. And similarly, X is a son of Y, but that doesn't mean Y is a son of X. Are you following? Therefore, this is not. Okay. Right. We will look at example where all things happen, but that's we will do that. Then R is transitive. That is, I can go from one place to another. Transitive. Here, if you say XY is related to R, and yz is related is R, then that means x is related to y and y is related to z. This is z. This should imply x is related to z. Yeah, do you follow that? Yeah. Now let's look at our real number example, less than relation. If x is less than y and y is less than z, then x is less than z. Yeah. Therefore, this relation is not reflexive, it's not symmetric, but it is transitive. Yeah. But let's look at the son of relation. It's that relation is not reflexive and it's not symmetric and it's not transitive. Why? If x is son of y and y is therefore and y is a son of z, that means y is also male. Okay, therefore y must be father of x. Okay, then x is a grandson of z, not a son, right? So that relation is not transitive. Okay, so your relation R is said to be is an equivalence relation on x if R is reflexive, symmetric and transitive. Yeah. Now we would like to see whether we have any such relation. Yeah. I'll look at the simplest relation. Okay. So we want to look at examples of equivalence relation. Okay. But before going, let me look at one more important relation. I'll come to that later. Suppose I have set x. Okay, let me call a set S. Okay, and x to be the power set of S. Right? And what are the elements of x? They are subsets of A and B, subsets of S. Then I define A is related to B if only if A is subset of B. That is, A can be subset equal to. It may also be B. You understand that? Okay. Now it will, if you want me to write, I can write it, but that's not very nice way. I only have to say A is a subset of B, nothing more. Right? A and B are subsets of X, yes, and A is contained in B. Okay, that's not very pretty, so it's better to define the relation like this. Okay, right. Now let's look at this relation. A is less than equal to. Now notice that it's a reflexive. Yeah, if A is a subset of B, and is it symmetric? If A is a subset of B and B is a subset of A, what does it mean? A equal to B. So in general, it's not true, right? If A is a proper subset of B, then B cannot be a subset of A. Yeah? So it's not symmetric. Is it transitive? Yes. If A is a subset of B and B is a subset of C, that implies A is a subset of C. Therefore, the containment relation is reflexive and transitive, but not symmetric. Okay? Please pause, review and proceed. These are the basic important examples you should be aware of. Now let's look at the first relation is give let x be any set, right? Let me look at the so-called diagonal subset, that is set of all x comma x. Okay, in x cross y, that is x comma y, where x equal to y, if you want. X cross x, so that x equal to y. This is called the diagonal set. So this is what my relation. Now, if you give me x1 and x2 in x, when x1 is related to x2, if and only if the ordered pair x1, x2 lies in R, that happens if only if x1 equal to x2. Yeah? So can you guess what is the relation? This is a subset R. So what is the relation induced by this subset? That is nothing other than equality relation. Do you understand that? So the relation induced by R on X induced by R is the equality relation. That is equality of elements. Are you following? And now this is a relation. Now let us ask, is it reflexive? Yes, x is related to x. Yeah, because x comma x belong to this. And if x is related to y, is y is related to x? Yes, if x is related to y is nothing other than x. Therefore, it's again same. Do you follow that? Okay. And if x is related to y and y is related to z, I want to know whether x is related to z. Yeah, but again that's easy because x is related to y, same as saying x is y. Y is related to z is same as saying y equal to z, right? But y equal to x, therefore x equal to z. Follow that? This implies this, if and only if. Yeah. So the equality relation is an equivalence relation. Okay. This is the first example. Understand this very well. Okay. Now let's look at an example which will be somewhat geometry. Suppose my x is R2, right? I am going to define a relation. See, in practice, very rarely one defines the relation by subset of x plus 6. Yeah, what one defines is give me 2 points of x and prescribe when they are related. Okay, x1 is related to x2 if something happens. That's it. That's the way we define. Okay. Even though the abstract definition of relation is R is a subset of x plus 6. The relation R on x is nothing other than a subset of x plus 6. And using that we define when two elements are related, x1 and x2 are related. That's what we did. Okay. Please pause on. Okay. If this abstract definition is a little kind of difficult for you, pause, rewind, go through it once again. Right? Because now I can't draw a picture of x plus 6, that is R4, right? So I am going to define, you give me 2 points x1, y1 and x2, y2. I want to know when they are related. I am going to say they are related if and if x1 equal to x2. That's it. I don't care what is y1. For example, 1 comma 0 is related to 1 comma 1, right? But 1 comma 0 is not related to 0 comma 1 because the x coordinates are different, or 0 comma 0. Even though the y coordinates are the same, but x coordinates are different. Do you understand that? I have to say whether these are related. So can you just quickly say when a comma b is related to c comma d? Yes, if only a equal to c. Very good. Okay. Now is this relation equivalence relation? That means is it reflexive if x1 y1 is related to x1 y1? Of course is true. And if x1 y1 okay related to x2 y2, does that imply x2 y2 is related to x1 y1? Of course yes, because if this relation shows x1 must be x2. If this has to be true, I have to make sure x2 equal to x1, but that's clear, right? Therefore this also somewhat is a transitive. I'm sure by now all of you know. I want to know whether it's related to x1 y1 is related to x3 y3. To show these two are related, what should I do? I have to make sure x1 equal to x3, right? How do I do that? Let's look at x1 y1 is related to x2 y2. That means this implies x1 equal to x2, right? And x2 y2 is related to x3 y3. Therefore this implies x2 equal to x3, right? But x2 is equal to x1 by the first condition. Therefore it follows x1 equal to x3. Therefore this follows. Yeah. Therefore this is a Equivalence relation, right? There are a lot more interesting example, but please look into the reference book which I had given, because for want of time I don't want to go into that too much. So because I want to give two. So we already have given 2 examples. So I want to give 2 more examples. Okay, this will be in number theory. Let me take x equal to z. Okay, fix a natural number. Let us say n equal to 5. Okay, fix any natural number, preferably n greater than 1. Okay, though it's not needed, but let me ask. Right? I want to define a relation. So you give me 2 integers a and b. I am going to say a is related to b if and only if 5 divides a minus b. You understand this? Now I want to say check whether it is an equivalence relation. When do I say m divides n? When I say m divides n, first of all m should not be 0. And then when I say m divides n, this is our definition. If and only if n is of the form k times m. There is a k, an integer, so that it is. You understood that? Yeah? Okay. Make sure, okay? Don't work out your long division method. Okay? Again, let me repeat. X divides y in integers, that means x is non-zero. Then, when I say x divides y, what should I want? I want my y should be a multiple of x. Where this multiple what? This is an integer, integral multiple of x. Do you follow that? Please make sure you understand, otherwise you will have problem. Okay, so everything happens only in z. Okay, no fractions, no real number, nothing. Is that all right? Okay, now the first thing, so does 5 divide 0? Because 5 I can write as 0 times 0. Do you understand that? Sorry, I'm very sorry. See, I get carried away. Does 5 divide 0? I would write 0 as some m times 5. So this m I can take to be 0. Yeah? Okay, I'm sorry for the goof. Okay, come back. So, the first, is it reflexive? Is a related to a? It is the same as saying whether a 5 divides a minus a, that is whether 5 divides 0. Just now I saw that, right? Yeah? Therefore, this is true. It is reflexive. 2. Next, if a is related to b, does it imply b is related to a? That's clear, because what does it say? 5 divides a minus b. That means a minus b is m times 5, where m is an integer. You follow that? Now, when I want to say, I want to know whether 5 divides b minus a. This is a question I am asking now. To show b is related to a, I have to show 5 divides b minus a. But remember, a minus b is this, therefore b minus a is minus m times 5. Right? Because this is negative of this, therefore I can write it as minus 5. Yeah? So what does it follow? Therefore b minus a is divisible by 5. Yeah? Therefore this is true. So what I have shown? I have shown it is symmetric. Okay? Now transitivity. Transitivity is also equally the same way. So transitive. Suppose a is related to b and b is related to c. I want to know whether a is related to c. Yeah? Right. Now if a is related to b, what does it mean? B minus a is a multiple of 5. Right? M times 5 or whatever it is. Yeah? Okay. Now let us look at b is related to c. What does it mean? That means b minus c. Oh, sorry, this is a minus b. And this is b minus c is some, let us say n times 5. Right? Now look at that. I want to look at a minus c, whether it is equal to something times 5. Yeah, this something is what I have to find out. But that's very easy. Can you see that how? Suppose I add here, what do I have? A minus b is n plus 5, b minus c is n plus 5. Therefore, if I add, I get b cancel. Therefore, a minus c is m plus n times 5. Yeah. So what have we shown? We have shown that this is transitive. Therefore, this is an equivalence relation. This is what is known as congruence relation in number theory. This is closely related to relation, equivalence relation defined by a subgroup of a group, but that can wait for your group theory class. Okay. Now the last example, this is another most important example. Usually this example is never discussed. Okay, but in practice, in my opinion, this is one of the most important natural examples. Suppose f is a function from x to y. Okay, just any map, any function. Okay, not necessarily one, not two, bijection, nothing. It's just a map, right? Okay. Now I am going to ask a question. So I am going to define x1 is related to x2 if and only if it takes the same value, f takes the same value at these 2 points. That's it. Yeah? Do you understand this? Let us look at some simple example to make sure that you follow that, right? Suppose f is from R to R and f of x equal to x squared, then what does it mean? So if I, 2 and 3, are they related? No, right? But minus 2 and 2 are related. Do you follow that? Yeah? Yes. Now suppose f is a, just for example, I'm just giving examples, whenever you look at this kind of definition, it's easy to look at some very easy examples to understand the concepts. Suppose f is from x to y is 1, 1, that is injective. Okay, when is x1 related to x2? If x1 is related to x2, if and only if fx1 equal to fx2. Do you understand this? Yeah? Yeah. But f is 1, 1. When this implies what? x1 equal to x2. You follow that? Therefore, if f is an injective function, 1, 1 function, then the relation induced by f is the equality relation. Okay, I should have put a PRP before, I forgot. If okay, please stop, proceed, review this and then proceed. Okay, come to the next example. Is this clear? Therefore, f11, the relation induced by f is the equality relation. What do you know about equality relation? We already know equality relation is an equivalence relation, right? Yeah. But what we are going to claim is for any f, okay, so we will call it x1 to say it's related x2 if only fx1 equal to fx2. Since I am going to deal with only this particular f, I will suppress this. I will only write x1 equal to x, right? I want to know whether it is reflexive. Yes, right? X is related to x because fx equal to fx. Very good. Is it symmetric? Yes. If x1 is related to x2, then fx1 is fx2. Therefore, fx2 equal to fx1. Therefore, x2 is related to x1. Right? Am I going fast? And is it transitive? Of course, yes. If x1 is related to x2, fx1 equal to fx2. If x2 is related to x3, fx2 equal to fx3. Therefore, fx1 equal to fx3. Therefore, it's a transitive. Therefore, this relation is an equivalence relation. Yeah, okay. So we have seen 4 examples. Please go through all these things carefully. Once again, equality relation, then you define a geometry thing, and the third thing is number theory, and fourth theory is functional oriented. This gives a variety of examples. You master these things, then you will be happy. You will be very confident. Right? Now, the closely related to the concept of equivalence relation is the so-called equivalence classes. So, let X be a set, and now I will assume this is an equivalence relation. Right? And fix a point X in capital X. Then this is the set of all y. Remember, this is going to be a subset of X. Whenever it's a subset of X, what should I do? You give me an arbitrary point of X, call it Y. I have to give a condition or a property which Y must satisfy so that it is an element of the set I want to define, namely this set. This is what I call equivalence class. Equivalence class of X, the element X. This is set of all Y in X, or if you want X dash, so that X dash is related to X. Okay. So if you give me a point A in X, when does it belong to the equivalence class of X? If A must be related to X. You understand that? Okay. Right? Have you understood? Let's look at some examples of equivalence class. In the first example is equality relation. What are the equivalence class? Equivalence class, if you say, let me write Y, okay? If Y and X, okay, Y is related to X in the equality class, that simply means Y equal to X. Therefore, this equivalence class is nothing other than the singleton X. Do you understand this? Please pay attention. This is a notation, this is an object we have defined. This equivalence class of an element. And we had identified that is singleton set X. Okay? This notation makes some other meaning. This notation has a different meaning. This notation has a different meaning. This is a subset, of course, of X. This is also a subset of X. We are saying they are equal. Right? Now let's look at the second example. That is a geometric example. We said x1, y1 is related to x2, y2 if only if x1 equal to x2. Right? Now let's look at a point A comma B in R2. I want to know what is the equivalence class of AB. What is this? This is by definition set of all xy. In where? In R2. With what relation? Xy must be related to AB. Right? But this is nothing other than when is xy related to AB? If only if x equal to A. Right? Therefore, what is the equivalence class? Can you see that geometrically now? So I have A here. Okay, this is my A comma B. Okay, and this is nothing other than the line x equal to A. This is nothing other than x equal to A line. You follow that? Yeah? Can you quickly say, if I ask another question, suppose I define a new relation x1, y1 is related to x2, y2. If only y1 equal to y2, and if I take AB, okay, let me use a different color. So I have x1, y1 related to x2, y2, if only if y1 equal to y2. Now I take AB. What will be the equivalence class of AB? That will be the line y equal to B. Yeah, just if you want, take it an exercise, discuss it. Okay, so PRP. Now let's look at the third. example requires a little bit of number theory. Remember, I said you give me A and B and Z, and A is related to B if only you 5 divides A minus B. That was my relation, right? The 5 can be replaced by any natural number greater than 1 if you want, but let me not worry about it. Let me stick to only 5. Okay? Now, I hope all of you remember the division algorithm. What does it say? You give a natural, any integer, I can write it as q times 5 plus r, where 0 less than or equal to r less than 5. Okay, q is also an integer. This is called the quotient, this is called the remainder. This is called the division algorithm. Okay, if you are not learned, you should learn it, because you will keep on using it everywhere, in particular in group theory and ring theory. In abstract algebra, this will be one of the standard examples, so you better learn this. Okay, division algorithm. Okay, there will soon be a video on that, but you can look up any book. Just assume that. So given any integer and okay, yeah, non-negative, a positive real number greater than 1 if you want. Okay, right? Suppose B is a natural number. Assume B is greater than 1, just then I can write as B equal to QB plus R. What is R? R should be less than, greater than or equal to Z, but B. So when I say it is divisible, what does it mean? A divides B, then R must be, the remainder must be 0. This is called quotient. This is called remainder. Right? Okay. Now this makes very interesting. Now notice that, so you give me this, give me A, I write it, okay, this is unique. Okay, this way of writing is unique. What does it mean? If you write A equal to Q1 5 plus R1, Q1 must be Q, R1 must be R. It's unique. That's another interesting thing. Okay, the whole thing statement is called division algorithm. Now suppose look at A. Now something very interesting happens. What is interesting happen? This A is related to this R, where R is like this. Why? What is A minus R? By construction, Q times 5. Therefore, A is related, right? You understand? Now, do you find something very interesting? Yeah. So, when is A related to B? Suppose I write B as Q1 5 plus R1 and A as Q5 plus R. What is A minus B? That is Q minus Q1 times 5 plus R minus R1. I hope I am writing it correctly. If A is related to B, that means B divides A minus B. And just now I said, if I divide this, that means the remainder must be 0. That means this must be 0. Notice that because of the uniqueness part of the division algorithm, I have written A minus B as something like Q dash 5 plus R dash, where R dash is, remember, R minus R1 should lie between. Okay. Are you following? With the loss of generality, you assume R is greater than or equal to R1, then R is already less than 5, therefore R minus R1 will be strictly less than 5. Do you understand that? That is your R dash. Okay? Therefore, if 5 divides A minus B, then R dash must be 0. That means R must be equal to R1. So what does it say? It says that A is equivalent to B if only if the remainders of A and B when divided by 5 are the same. Remember, our remainders have to be 0 less than or equal to R, less than or equal to 4, strictly less than 5. Okay, please pause, review. If you have not seen division algorithm, this may be slightly tougher, but it will be nice example to learn. Okay, don't miss it. Please discuss with your friends, or if necessary, you consult your teacher. Learn this example very well. Okay, have you understood this? So we have found out the equivalence class. Therefore, what is the equivalence class of A then? Equivalence class of A, therefore any B therefore must be pi times Q plus R, where 0 less than or equal to R less than 5. Do you understand that? Yeah, sorry, pi times. I'm sorry, I'm going fast. That's why I'm making mistakes. Yeah, right. So A minus B is pi times Q. Therefore, what should be B? B equal to A minus pi Q. Therefore, if I say, okay, B belong to, or oh, I should say B, right? Sorry, I'm sorry for the thing. What I'm writing is correct, but it's good. Suppose B belong to A. What does it mean? B minus A must be multiple of 5. That means B must be A plus pi Q, right? Therefore, so you start with A. So start with A, then A plus 5, A plus 2 times 5, and so on, and A minus 5, A minus 2 times 5, and so on. Do you see the arithmetic progression? Okay. So traditionally in number theory this is called a congruence class, but okay. Yeah. So for example, what will be the equivalence class of 1? Equivalence class of 1 will be 1, 6, 11, subtract 5, therefore minus 4, subtract 5, minus 9, and so on. Okay, PRP. And the last example equivalence class is easy. This is x to y. So what is the equivalence class of x? Equivalence class of x, suppose fx equal to y naught, let us call it b, right? Then equivalence class of this is nothing other than f inverse of singleton b. Do you remember in the last lecture we defined what is the inverse image? Yeah, why? Let us look at it. If x dash belongs to singleton x, what does it mean? Fx dash equal to fx, but fx equal to b. But fx dash equal to b, that says x dash belong to f inverse of singleton b. Yeah, you follow that? Conversely, if z belong to this, that means fz must be equal to b. But this b is nothing other than fx. This means z is related to x. That means z belong to the equivalence class of x. Do you follow that? Please pause, review, and proceed. Okay. Now, I don't know how much time I have. Let me have a look at. Oh my gosh. I forgot to switch down. Okay, no problem. I will. Right? So we are defining equivalence classes. The first observation one makes is, if suppose x is a set, this is an equivalence relation, then you give me equivalence class of x and equivalence, let me call it equivalence class of a, equivalence class of b. A and b are x. Then either they are disjoint or they are equal. Okay, look at the earlier examples, you will see. For example, let's look at the geometry example, just it will be fun, right? So equivalence class of a, b, and suppose I take equivalence class of c, d, right? If they have a common point, right, suppose x, y belong to both, right? What does that mean? X must be equal to a, you understand? And similarly this belongs to that, therefore x must be equal to c, therefore a must be equal to c. You follow that? Yeah, that is the trick. So please understand, this is very easy. Suppose x belong to, if this is empty, there is nothing to prove, right? So what happens? Either this must happen or this must happen. You understand that? P or Q. This is logic. When is P or Q true? If either P is true, okay, one of them is true. If P is true, then it's PRQ is true. Okay. Suppose P is not true, then what I should prove? I should prove Q is true. Do you see the logic? This is the reason why we want us to spend time in understanding logic. When is PRQ true? If one of them is true. If P is true, then it's true. Nothing more to do. Suppose P is not true, then I have to prove Q is true. Do you follow that? So, you give two equivalence classes A and B. If they are empty, there is nothing for me to prove. Alright? So, let me assume that's false. If it's false, what does it mean? That means X belongs to equivalent class of A and B together. Right? Now, what does this say? This says that X is related to A and X is related to B. Right? But due to reflexivity, this is same as saying A is related to X. This is reflexivity and X is related to B. Right? This is reflexive. Okay, this X related to A implies A is related to X and X related to B, let me keep it as that. Now, what do you think I should use? I should transitivity. That will mean A is related to X and X is related to B. That means A is related to B. Yeah? Right? Very good. Therefore, A is related to B. This is the first observation we make. If the equivalence classes A and B have non-empty intersection, the first observation I make is A is related to B. Since it's a symmetric, B is also related to A. Is that clear? Now we are through. I want to say this equivalence class of A is contained in equivalence class of B and equivalence class of B is contained in equivalence class of A. If I prove one, the proof is similar. Right? So let's start with the Z in this equivalence class. That means what? Z is related to A. But I know A is related to B, therefore Z is related to B because, are you following? Z is related to A because it belongs to this. Right? Okay. But we already proved is the equivalence classes have a non-empty intersection, therefore A is related to B. Therefore, A is related to B. By transitivity, this implies Z is related to B. That means Z belongs to B. That means equivalent class of A is a subset of equivalence class of B. Now interchange the role of A and B, you get equality. Okay, path, review, see. Okay. Now, this fact gives rise to a partition. So, any equivalence relation gives rise to a partition of X. So, let's start with X. Let's look at this X. This is an equivalence relation. Right? So, for each X, look at this equivalence classes. Therefore, let me look at the collection of all equivalence classes. Okay, remember this is set theoretic notation. I hope all of you remember if I write as a set 2, 3, 4, 2, okay, 5, then this set is nothing other than 2, 3, 4, 5. I may write it, but as set is a collection of only distinct elements, therefore this will not be there. You will follow that? Why I am saying this? Why I am saying this? Let's look at our earlier example A, B in R2. Then 1, 2, the equivalence class is same as the equivalent class of 1, 0 or the equivalent class of anything of the form 1 with anything here. You follow that? So they will be counted multiple times, but we are not doing that. We are taking only equivalent classes which are distinct. Okay, this is set of distinct equivalence classes. Okay, I want to say they form a partition. Before that, we will define a partition. Let X be any set. Okay, a partition is a collection of subsets such that 1 X is union of AI. We had already defined arbitrary union. Do you remember that? Because I do not know what is the index set, whether it's finite, infinite, countable, uncountable. If you know that word, I don't know. That's first condition. Second condition is if I, the indexing set, the indices I and j are different, that implies AI is different from AJ. AI and AJ are disjoint, not different. AI and AJ are disjoint. We will assume that these are all non-empty to avoid trivialities. Okay, any partition is a collection of non-empty subsets A of X with what property? X must be union of AI's, and 2, whenever the indices I and j are distinct, AI and AJ are disjoint. Right? Now go back. This is the definition of partition of the set. Now let's look at X with an equivalence relation. Then let's look at, okay, this is my collection. What is the collection? X. X varies over capital X. This is a collection of distinct equivalence classes. I look at one particular example before I finish the core lecture. This is okay. Now I want to say this is a partition. That is it clear why X is union of these elements? Yeah, why? Because give me any X, it belongs to the equivalence class defined by X, right? Yeah, but there is a subtlety. What is the subtlety? Suppose you give me a Z, right? Now Z, there is an equivalence class of Z, right? Now this is a collection of all distinct equivalence classes, right? So this class may be there, but Z may not be there. Okay, you understand what I mean? Maybe I should look at the example. Let us look at again geometry example R2. Okay, now let's look at this. This is my 1, 0. This is my 1, 1. Right? Now my Z is 1, 1. Right? But the equivalence class I have chosen for this is this. Let me define AX equal to set of all X, Y, where Y is allowed to vary but X is not. Do you follow that? So these are all the lines, okay, vertical lines passing through X, 0. Follow that. Now the equivalence class of, we have seen the equivalence class of X is, the equivalence class of X, okay, X, 0, this is the equivalence class of X, 0, right? But are you following? This is the equivalent class of X, 0. Therefore my partition I would have taken only as X in X, X is in R, right? Now you give me the point 1, 1. My point 1, 1 is Z, right? Now I want to look at the equivalence class of Z. But equivalence class of Z is nothing else than X, equivalence class of X, 0 if when Z is X, Y. Right? That is 1, 0. You follow that? Yes? Right? Therefore, come back. Therefore, give me any Z, it has to be in one of these elements. And just now we proved these distinct equivalence classes do not have any intersection. Therefore, this gives rise to a partition. Okay. So, if X is a set, this is an equivalence relation. The equivalence classes, okay, distinct equivalence classes. Okay. A set of distinct equivalent classes, okay, is a partition. Now let's look at this example Z with our 5. Then you can see the equivalence class of 0, equivalent class of 1, equivalent class of 2, equivalent class of 3, equivalent class of 4. These are the only equivalence classes. Z is the union of this. Why? Give me an area A here. When I write it as Q5 times R, this R has to be either 0 or 1 or 2 or 3 or 4. You follow that? Okay. I am going fast. I went fast actually. Please review this. Discuss with your friends. That's the best way. Okay. Since I wanted to finish in 4 lectures, I had to go a little fast. Maybe I should have cut down 1 or 2 examples. But then, as you can see, all the 4 examples of different kind, they give a very good idea about how to work with those. Okay, one is number theory, one is geometric, another one is abstract, the third one is equality, with which we all started doing mathematics, right? Okay, so I hope there is a variety. I know I went fast, but please discuss with your friends, and the best way is pause, review again. Okay, take care, stay safe, we will meet again.